Well, I'm surprised by how much the program has improved since last fall. It seems, we're talking to people at Google, that they increased in strength by about 20 ELO to 100 ELO a week.
So this is a testament to the power of the reinforcement learning part, right? And to the power of the representation, what the deep neural network can represent in terms of the evaluation and in terms of the move selection.
It's striking, because we've seen many, many games.
Yeah.
Checkers, and chess,
and go up to now.
Incremental, steady progress. Actually, I want to say that the most amazing thing about it, I think we don't want to miss the base amazing thing, which is that it's been an enormous jump in performance. No other game has been like this. Like, chess, we figured out search, and then, there's a long period of waiting for the computers to get faster.
Yeah.
And so this, like a year ago, Go programs, there were, Martin should say what the status was.
Yeah, they were 4 or 5 levels weaker than they are now, maybe 6, because we don't really know the limits of strengths of the current version. Right?
So in the fall, it was the first time ever we had professional level play by programs.
Yeah.
And now, today, maybe they're beating the world champion.
So in my view, all the modern heuristic search programs have these 3 components. There's the search, there's the simulations. Those are the 2 things we had when we started this Monte Carlo tree search, right? And the third thing is the knowledge. Mm-hmm. So in the old days, we had the other 2 components. We had the search and the knowledge. In the early days of Monte Carlo, we had the search and the simulations. And now we have all 3 components, and they kind of figured out how to put them all together. And that's what makes really for the quantum leap in performance.
Where by knowledge you mean
it's the machine learned,
the learned evaluation,
self-play.
Yes,
and
which is it's also a deep neural,
which has the representational power to represent all this complex knowledge.
That's what I think is the key piece. I mean, we knew we could get knowledge from self-play, but we didn't know how to distill it down. And if you're going to talk about millions and billions of games, then you really have to think about how to distill that down in a way that you can use it quickly. And that's where the deep learning piece comes.
And it's not just a database, like some of the commentators on TV kept repeating, oh, it just has such a big database. It doesn't. It distills all that into some knowledge representation.
The patterns are coming from a neural network, the learned weights of the neural network that laid over the board every place. That's the convolutional part, and exploit the symmetry. But at the same time, of course, you have to understand the bigger structure of the board, the position as well. And put everything together.
But isn't that the deep part of
interesting? That's where the deep part is.
So my understanding is that Computer Go was thought to be different. All these other previous games, we relied on having good knowledge, a good static evaluation function. And that, I don't know, isn't it true, Martin, that the conventional wisdom up to
last
year or so.
Monday.
6 months ago.
Up to AlphaGo. Was that evaluation functions.
It's hopeless.
It's hopeless in Go.
Yeah, that's true. And I think evaluation functions were hopeless with the previous ways of building them. And now they seem to have a very good evaluation function. And that's a huge advantage, a huge difference.
So it was a natural idea. It had been around, but it hadn't worked in Go.
Nobody knew how to make it work, and not for lack of trying.
I think that, as we've seen with machine learning in general, we need a certain amount of computational power before it hits a ramp where now things accelerate.
This is what I was thinking about 10 years ago when first we were working on MCTS, Monte Carlo tree search. We didn't have the computational power to get any of this if you would add self-play at the time, or even 5 years ago. I'm not sure.
So to me, it's kind of how they engineered this algorithm with lots of different pieces. It's not just that they had access to lots of different computing power.
It's a very, very complex system, and it's supremely well engineered.
Yeah, and Ajia Huang must be in heaven, right? He worked in our lab when he was working on Computer
Hex.
Go and Hex. And there were 3 of us. And now he's at DeepMind, and there are 20 people working on the same project, probably more. And they've got all these different areas of expertise. And they've figured out how to bring everybody's piece of expertise to attack this one problem.
So it's the Bell Labs of artificial intelligence.
I don't know what it is, but it's a fantastic place to be if you're a Go programmer right now.
So we should explicitly give them the shout out. It's an enormous accomplishment, and we're very proud of them, but they did it. We set them up, we taught them a few things. It's an amazing thing that they've accomplished.
Now we get to watch.
You wanted to solve Go, and that's why you came to Alberta. That's because of you.
And because of you, because he wanted to solve Go with reinforcement learning, and in
because
the
of
end,
yeah.
that's what happened, but not while he was at Alberta. Because at that time, we didn't have the third piece of the puzzle, which is this deep networks, right?
But
So-
he pulled together some of the pieces.
Yes.
Well, Monte Carlo Tree Search came along while he was here, and Shaba, of course, played a triggering role in the success of that.
So he was learning evaluation functions using reinforcement learning for the game of Go, but using extremely simple features. So his features at that time were 1 by 1, single points, 2 by 2, and 3 by 3, and that was it. So he did the best he could with that representation.
They still use those.
Yeah,
in
and I think
AlphaGo.
But-
I think what's interesting is ultimately what deep learning brought was to figure out how to hire to rebuild them. And it's not surprising. We've seen this in many cases. There's huge power in hiring.
Part of its success is it can afford to have a very, very close-looking game and be very happy that it's going to win.
It'll win.
And close-looking games are really hard for humans to score. Like, am I ahead or am I going to win or not?
One of the best Go players in the 70s, his name is Ishida Yoshio, and he was famous for his endgame capabilities, so he would do this same thing. He would try to keep the game very close, and then he would just win by better endgame. And guess what his nickname was in the 70s? The computer.
Okay.
It took an effort to translate the ideas over from Go to Hex. It was not straightforward. I think the first 5-6 things he tried didn't work, and eventually,
It's true.
Being Archer, he kept working and he
Yeah.
kept working and he kept trying things, and eventually he found a way to use the pattern-based simulations to make them work for the game of Hex, and that was the jump in performance that you saw.
Yeah, 200 elo.
That kept your Hex program the best in the world.
Yeah. It was a fun time in our group then, because there was Aja, there was Jakub Pavlevich was around, Broderick Arneson was still around. So yeah, we had lots of different people. We were throwing lots of different ideas at things, and you got to throw 10 ideas at something, maybe one will stick.
That's how progress works in science, right?
Yeah.
It's not. If you look at the Nature paper, that's the slick final result.
Yeah, that's amazing.
What they didn't publish is the huge mountain of work
Yeah.
and failed experiments
Yeah.
and frustrations and other things we tried that
Yeah.
didn't work. So that
Yeah.
what you see in a high-level result is the tip of the iceberg.
Yeah, and that's
The
amazing.
10% or less than 10% that actually worked.
So their iceberg must be huge, because there's like 10 different ideas in that paper that are really nice. So tell me a bit about Mark and what he did when he was with you.
Yeah, so Mark was part of the poker group. He was a little bit, he played a funny role. He wasn't actually directly involved in us building competition programs. He was actually looking at exactly the problem: how do you take our techniques and start thinking about them for other problems? So he wanted to look at, what of the poker-specific knowledge might we have added in, and so how would it work if the games had different tree structures, different kinds of information structures, which types of techniques would work, and he pioneered, through that he pioneered more general sampling techniques, which, the funny thing, immediately then filtered back into the poker side of things. Some of the sampling techniques he built were what we were missing in No Limit. It turned out that we couldn't handle a certain kind of growth in the tree, and while he was trying to think about them generally, it comes back and now becomes one of the dominant techniques for the No Limit game. I think one takeaway is just realizing just a mindset of realizing that AI is accelerating very fast. I think this general conception of just thinking about the last few years is just, and not just this DeepMind's accomplishment, but their work in Atari and taking what we had set up with a framework to do reinforcement learning, and then just jumping what I thought was going to take 5 years, doing that in the realm of a year or two.
So fast.
Yeah, things are moving very quickly, and this is
fast.
a super exciting time to be doing AI. And then to think that we could do that with evaluation functions and learning and learn all of that whole architecture up, I think that's super exciting, and is how we're going to see this, I think, get out to other problems. Is we're going to see it happen because someone's going to realize, oh, I just have to pose my problem. I'll just pose my problem like that, and
We
then
have a new hammer.
Yeah.
Yeah, it's like machine learning now is almost like arithmetic. A lot of these companies who are hiring, it's like, well, you need to know math, you need to know stats, you need to know how to code, and you need to know machine learning.